if you do not have any question, then you can please mute your mics. And if there is a question, you can unmute and ask anytime. Okay. I hope this other part of the course is going fine, and the topics there are quite different from the topics that we studied. Is that right? That
Yes,
is
Yes, sir.
about communication, and communication part is over or is yet to be completed.
so main
Hello.
part is just started. Earlier
Okay.
we were doing history part.
Yeah. So this course is about mainly about understanding the background, understanding a bit of physics, and so that's why we also devoted quite time to study the electronics and now we have discussed in detail the diode uh, physics, and in the last class, sorry to sort of interrupt because interrupt your current flow of ECN101 because there it might be a different course. But if you recall from the last class that we had on devices, it we tried to understand the idea of transistor in a bit detail, and we saw that the transistor can be of two types actually, or the transistor can be realized in two ways. One is when the current is transferred from a low resistance part to a high resistance part, and second is by having this kind of black box device which has IV characteristics like this, and if the IV characteristics are like this, in which the current between two terminals, between these two terminals, as a function of the voltage across these two terminals, if this current can be controlled by a third terminal, which is essentially the gate terminal, in this way, in which a small change in the gate voltage can result in a large change in drain current or the current across two other terminals, then this device can work as a switch and as an amplifier. So there are these two ways to implement the transistor nowadays, and this is essentially BJT and this is the MOSFET. And what is a transistor? Transistor is a device through which we can achieve switching and amplification. So please remember that. That transistor is a three-terminal device in which switching and amplification can be achieved, and uh, one of the terminals can control the current across the two other terminals. Any doubt, anything that you would like me to repeat till now? If not, we also discussed a bit of bipolar junction transistor, and as I said in that class also, that the BJT was the first transistor, so to say, and the first transistor was in fact the point contact transistor, which is another form of BJT, and uh, in that case, we have three semiconductors put in such a way that there are two junctions now. There is this PN junction and NP junction, or NPN. There are these two junctions, and one of the generally what happens is that one of the junctions is forward biased and the other junction is reverse biased. But that is in our hands actually, because we can apply external voltages, and so biasing is in our hands. When one junction is forward biased, the emitter base junction is forward biased, and the collector base junction is reverse biased, in that case, the amplification is achieved as we expect from a transistor. But we can bias the transistor in such a way that both the junctions are in forward bias, or both the junctions are in reverse bias, or the collector base junction is forward bias and emitter base junction is reverse bias. So there is in total there are these four possibilities. So we can do anything that we want, and there are some applications as well. Some applications of BJT where these other kind of biasings are done. For example, there are some cases in which both junctions are forward biased or things like that. But the amplification that we expect is not achieved in those cases. Although when the collector based junction is forward biased and emitter based junction is reverse biased, in that case, the amplification is achieved quite like when emitter base is forward biased and collector base is reverse biased. But again, the amplification is not as high as uh, it is in the case when emitter base is forward and collector base is reverse. Uh, so I guess this basic mechanism of BJT is also clear to all of you. Let me quickly review that as well. In BJT, what happens is this emitter is, for example, a P-type material, base is N-type material. This is forward bias, which means that there will be a diffusion of majority carriers. So there will be a lot of holes that will go to the base terminal. At the same time, this base collector is reverse biased and base is N-type material. And the holes coming from the emitter side, they become minority carriers in the base terminal. And since this base collector junction is reverse biased, so the current here will be just the minority carrier drift current. And the minority carriers are what now? The minority carriers are the holes coming from the uh, this emitter junction. So now the holes that were coming from the emitter junction, they now become minority carriers in the base, and they are swept by this reverse bias junction to the collector side. And if you remember the IV characteristics of the junction, the resistance of a forward bias junction is small and the resistance of a reverse bias junction is quite large. So what it means is that the current has been, or the charge carriers have been transferred from a low resistance region to a high resistance region. Okay, so that's how this amplification is achieved in the BJT. Now the output voltage will be high on the collector side. So here we have looked only one component of the current. And what is that component? We have only looked at the current that uh, current due to the holes coming from the emitter side. But on the junctions, as all of us know, that things can be quite complicated. So, and that's what happens here as well. That that apart from this holes coming from the emitter to base, there are electrons going from base to emitter as well. These two are the majority carrier current components. Apart from that, there will be this minority carrier current as well, and uh, so all those kind of components will also be there that are there in a simple PN junction. So on both junctions, both majority and minority carrier currents are there. But the major current that is there is because of the holes that are coming from the emitter to the base and then to the collector side. And more the number of holes, more will be the current at the collector terminal. So this plot here is the plot of IC versus VBC as a function of IE. So as you see that IC does not depend quite much on VBC, which means it does not depend on the base collector junction voltage. It's a reverse bias current, so it's almost independent of the applied voltage. However, it depends on how much current is coming from the emitter terminal. So if the emitter current is more, collector current is also more. If emitter current is less, collector current is also less. And it is almost independent of the base collector voltage. Now, there are few important things here. There is this base width, also termed as WB. So to have a good PNP transistor, to have a good amplification in the transistor, we generally prefer that almost all the holes that are injected from the emitter terminal, they should be collected to the, they should be collected at the collector terminal. So which means that the recombination in the base should be minimum. And what should we do if we need to reduce the recombination in the base?
So less doping.
Less doping one. What else?
So thin region.
Possible to decrease the length.
Decreasing length, yes. Yeah, you're right. So in order to reduce the recombination, we need to reduce the number of electrons that are coming from the base side. And in order to do that, also we need to reduce the time spent in the base terminal. The time that the holes spend in the base terminal should also be reduced. And that's what we try to do in order to reduce the number of electrons coming from the base terminal. We reduce the doping of the base terminal, and in order to uh, reduce the time that the holes spend in the base terminal, we reduce the width of this base junction, or width of this base part of the device. And there is this, generally there is this uh, this relationship that we try to maintain. WB is the base width, LP is the mean free path of the holes. So what is mean free path? It is the average path or average distance that the holes travel before they collide with somebody else. And generally, once the holes collide with somebody else, then it is highly probable that they might recombine. And it depends on multiple factors. It depends on the doping concentration. It also depends on the dielectric constant of the material. Okay, so the thing is that we generally try to ensure that the base width is less than the diffusion length of the holes. So we try to make sure that the holes that are getting injected into the base terminal are crossing the base terminal without any collision. Okay, and directly to the, so there is a less probability of them being
So,
recombined. Yes.
sir, if VBC is 0, then how IC can be present?
VBC, sorry, what is your question? If
If
VBC is
equal to 0, then how IC is
Yeah.
having that value?
Yeah, so somebody would like to answer that?
So actually this IC is coming from the IE part. Some part is going to IB and some is going to collector part.
Yeah. So this IC is actually the reverse current in this case, as you see. And so if we just look at this base collector junction, this is a good question, I would say. If we just look at this junction and if we assume that this emitter is not there, in that case, what happens is when VBC is 0, which means equilibrium, no voltage applied, in that case, the minority drift is equal to majority diffusion, which means that there is a minority current, but it is balanced by the majority diffusion current. Okay, so the net current is 0. But now what is happening is that this junction is not alone. There is an emitter as well. And this emitter is injecting current into the base, which means that it is now increasing the minority current in the base. So that's why there is a net minority current that is there because of the IE current. So even if VBC is 0, because now the minority carriers have been more in number, so that's why this IC is also non-zero, because additional minority carriers are being pumped into the base. So the majority diffusion is not able to balance all the minority drift, because now minorities in base are coming from the emitter terminal. Is this clear?
Yes, sir.
Excuse me, sir.
Yeah.
So do the depletion region of the two depletion region collide or like they overlap?
Yeah, that might also happen in some case, and that is actually known as the punch-through case in the transistor, in which so generally because of the base emitter junction, because of this VBE, this because of the forward bias on base emitter junction, this depletion width is getting smaller and smaller. But what can happen is that because of the reverse bias on the collector base junction, this can be so much that both of them actually punch through. And so that is also the case in some transistor, and it has application in some cases whenever the base current is not so important. But that is not always desirable to have. Actually, we generally want this base region to be thin, but we do not want it to be zero, because in that case, this current, majority carrier current, uh, becomes zero in the base, or becomes very small in the base. So this control of the base on the total current is actually taken away if this punch through is happening in the case. Although that is desirable in some optical applications, or in some specific cases, but not always. Now, yeah, there is any question?
Yes, sir, one more. So this IB is due to electron flow or a hole flow in base?
No, this is the electron current.
Okay, sir.
So the electrons are getting injected into the emitter from the base, and these electrons are being taken from the battery. So that's why there is this IB current there, because of the majority carrier. Now, my question to all of you is that here the current, actually, if we just look at the transistor action, we are generally concerned about the current across the collector terminal, and the base terminal becomes like a control terminal in this case. So the question is, how is base controlling the current in the transistor, in the BJT transistor? Okay. And if you understand, I would say that if you understand this part, how is base the control terminal, then I would say that you have understood the most of the transistor, or most of the BJT thing. Okay. So just think about it. How is the current being controlled by the base terminal? Although we are mostly concerned about the current from going from emitter to collector, but still the base is the control terminal. How is that so? Does anybody know this or not?
So this base terminal controls the it acts like a gate because it controls the depletion region width of the emitter base region. So this controls the flow of holes from emitter to base, and then it controls the flow of current through collector. Because we are
Yeah.
providing, sir, minority, we have to provide minority carriers in this base region so that they can flow in reverse bias in this collector region, and this is provided by emitter, and which is controlled by the this biasing of the emitter base region.
Yes, that's right. That's right to an extent. Anybody else would like to add to this? Uh, Actually, being in electronics branch, I would say it will be it's a good idea to take interest in electronic devices. Although uh, not everybody would be interested in this, but it's always good to understand what you are reading, what would be your core subject. So that's why I would request most of you, or I would expect more questions or more comments from your side. That would be better for general understanding. It will be even better for me as well. It will help me better in delivering the class. So as Dikshant said that without base terminal, this emitter base barrier cannot be properly controlled. And the emitter current depends on the, if you remember the band structure of the junction, there is a barrier between P and N type material. And by controlling the height of the barrier, the current diffusion current is changed. So this base current or this base terminal has an important role in controlling that barrier. In addition to that, there is also a relationship, a mathematical relationship between the base current or number of electrons injected to the number of holes injected, and that depends on the relative doping of these two materials. So these two currents are also highly correlated. The electrons injected from base to emitter and the holes injected from emitter to base, these two things are also correlated to each other. So that's why this also needs to be there. This injection of electrons from the base to the emitter is also essential. Although this base might look like a tiny thing in this transistor, but it's also an important quantity. So what I would say is that in order to make a good transistor in which a maximum current is delivered from emitter to collector, we need to have a thin base, we need to have a lightly doped base. At the same time, we need to have a lightly doped collector as well, so that this reverse current is also less. Because on this junction, there will be a reverse bias minority current, and in order to have its value to be too small, its value be small, we need to have a light doping on the collector side. So emitter is the most heavily doped, so that's why it is shown by P plus here. Second comes base in doping, and third is the least heavily doped is collector. And that's why there is only P written on the collector side. And finally, what I would like to say here is that uh, ultimately, if we properly understand the junction things, if we properly understand how a PN junction works, how various components work, it's extremely easy to understand a BJT transistor. So it's a direct generalization of the discussion that we did in PN junction. Although FET MOSFET will be slightly different, so we need to understand it slightly differently. But this BJT is a natural generalization of the PN junction discussion. So that's why what I would suggest is that uh, that you all of you go through these things on your own now based on your basic understanding of BJT and your understanding of PN junction. And what are these things? These are different regimes of operation of BJT. Different regimes mean when base emitter is forward and collector base is reverse, it is known as the active regime. When both of them are reverse biased, it is known as the cutoff regime. And when both of them are forward biased, both the junctions are forward biased, it is saturation regime. When collector base is forward and base emitter is reverse, it is inverse active regime, as if it is inverse of the active regime. So I would suggest all of you to go through what would happen in these four regimes. And it's not so difficult to understand. Uh, Apart from this, on this slide, we have a PNP transistor whose theory we have discussed a little bit. And on the right side, we have NPN transistor. So, which will also be quite similar to the discussion that we had in about the PNP transistor. Now, these are the IV characteristics of the BJT. And if you recall, uh, so if you, so let me, before going into the IV characteristics, let me show you the configuration. This is the configuration. We have base, emitter, and collector. And it's the transistor is in active regime. It's in common emitter configuration What do we mean by common emitter? In common emitter, uh, the emitter is common to both input and output side, which means that if we are applying an input voltage on base terminal, emitter will be common to the base as well, and output is being taken across collector emitter. Okay, so that way emitter is common to both input side and output side. So that's why it is known as common emitter configuration. There can be common base configuration as well and common collector configuration as well, but we will not discuss them here because we do not have much time. In fact, we do not have any time left. These are just extra classes. Compensatory, I would say compensatory classes. I could not take some of the classes in between. So in common emitter configuration, this base emitter is forward biased and base collector is reverse biased, active regime operation. Then what would be the characteristics on the input side? On the input side, which means between base and emitter, it's a forward bias junction. So the characteristics will be pretty much similar to the forward bias characteristics of a PN junction, like this. I hope this makes sense. IB versus VBE will be like forward bias characteristics of the PN junction. And for different VCE, uh, there will be slight different in the characteristics because slight number of change in the carriers are there. However, this is more interesting. This is the output characteristics. This is IC versus VCE. And what is this? How does these characteristics look like? These output characteristics. These are the input characteristics. These are like just like the forward bias junction. These are the
Sir,
output characteristics.
logarithmic sort of graph which gets constant after a time.
Sorry, you were not properly audible. Please repeat.
Sir, it seems like a logarithm sort of graph. I'm not sure though.
Logarithm. Okay.
Looks
Anybody
like
else?
reverse bias.
Sorry, your voice seems to be.
Reverse biased, but in first quadrant.
Now, why do you think so?
Oh, sir. No,
But
sir. I've made a mistake.
no, you were right, in fact. But I would like to know why did you make that mistake? There might be some reason for that. But you are right. I would say you were right.
Sir, because in these there is no breakdown region. So then I said I had made a mistake.
No breakdown. We are not going up to that kind of voltages, so that's why there is no breakdown. Okay, it was just a guess from your side. Or was it more than a guess?
Sir, instinctive understanding, I could say.
Okay, so this is how the reverse bias characteristics look like. If you recall the reverse bias characteristics, and these are the IV characteristics for different uh, lighting conditions. These were the characteristics in the case of a solar cell. In this third quadrant, if you see that if the minority carriers are more, here the minority carriers were more in the case of solar cell because of the light. But now in this case, minority carriers will be more because of the more emitter current or more base current, which are both of them are related to each other. So in that case, and if we flip this, if we take a mirror image of these characteristics, or if we bring these characteristics in the first quadrant, this is how they look like. For different base current values, this is how the collector current will look like, because collector current is the reverse drift current, depends on the minority carriers, and the minority carriers depend on the emitter current, which depends on the base current as well. So that's how this is coming from. So I would like you to devote some time and think about it, how this output characteristics of the BJT is coming on, and that will give you quite an insight into this whole functioning of the BJT. Okay, so generally in BJT usage, draw uh, we always try to draw the input characteristics, which is the IV relationship at the input terminal, and the output characteristics, which is the IV relationship at the output terminals. Okay, so I hope this part is more or less clear. I would like you to think more about it and try to understand these things. These things will be there in your second year devices core in more details. But just to have a basic idea of an operation, it's good to go through them even at this stage. So now we'll see uh, or we'll try to understand a more, I would say, a more important transistor, which is known as the metal oxide semiconductor field effect transistor, or MOSFET. So nowadays, most of you would also know that MOSFETs uh, have almost replaced BJTs in most of the electronic appliances. Only in high frequency and high power applications, at some places BJTs are used, but for all the normal applications, MOSFETs are used. So even in our cell phones or laptops, uh, almost all the transistors are the MOSFET transistors. Okay, so and there were good reasons to do that. One of the reasons was that a large number of MOSFETs can be integrated on a single chip. So this integration is easy in the case of MOSFETs as compared to the BJT. BJTs are also big in size because uh, this depletion control needs to be done properly. Uh, so let's now try to see how a MOSFET work. And the key term here is the field effect transistor. And what do we mean by field effect? Anybody knows this? What is the meaning of field effect in MOSFETs? In the name of the MOSFET, metal oxide semiconductor show sort of tells the material out of which it is made of, and field effect tells us about its physical mechanism. Anybody knows what is the why field effect is there? Yeah, you can make a guess as well if you want.
Maybe because the junction fields play an important part in this type of transistor.
Junction fields. Okay. Anybody else? Anybody else wants to? Yeah, it was a guess, I would say, although it was not a. Uh, so there is a field that is playing a role here. Uh, just hold on for a moment.
So is it something to do with the electric field? I'm guessing from the diagram.
Sorry, I was somebody came. Yeah, you were saying somebody said something.
So is it something to do with the electric field? I saw another diagram of MOSFET on Google, and that gave me some
Yeah,
idea
yeah, you
about.
are right. So yeah, so you are right that the field means electric field. So somehow the electric field plays quite a crucial role here, and that's why this name is there, field effect. Uh, and this field is not so important in BJTs. This electric field is not so important in BJTs. But as one of you told that it is not the junction field actually, it is the electric field created from the gate. So let's see how it works. First, let's try to understand what is a MOSFET. MOSFET is like any transistor is a three-terminal device. And the three terminals here are, one is the source, second is the drain, and third is the gate in this particular figure. Uh, Also in this picture here, there is a source, there is a drain, and there is a gate. Apart from these three terminals, there is a fourth terminal as well. But this fourth terminal is most of the times grounded. It's almost all the times it is grounded. It is known as the body terminal or the substrate semiconductor. And the architecture of the MOSFET is like this. There is a p-type substrate. Then there would be these two terminals, source and drain, they would be of opposite polarity. So if the body is p-type, the source and drain will be n-type. And if the body is n-type, the source and drain will be p-type. Okay, they should be of the opposite polarity. And the third terminal, the gate terminal, is almost a metallic gate. It's either heavily doped semiconductor or in most of the cases it is a metal. There is an important thing here. The third terminal is not connected to these two terminals directly. There is an insulator between the gate and the semiconductors here. And this insulator is silicon dioxide, SiO2. So in a way, we have a metal, gate metal, an oxide, and a semiconductor. And in this semiconductor, we have two contacts, the source and the drain. And that's how this MOSFET looks like. And that's why this name is there, metal oxide semiconductor, which means gate metal, oxide insulator, semiconductor is the actual semiconductor. Silicon, most of the times it is silicon. And in this semiconductor, we have the two other contacts. Okay, and field effect means that the electric field due to gate, so we apply a voltage on gate terminal that creates an electric field, and that electric field is extremely crucial for this transistor to operate. So the way this happens is that generally if there is no voltage applied anywhere in the device, generally what would happen is there will be a small PN junction here, there will be a small PN junction here. And this is a p-type material, so there will be number of holes will be more as compared to the number of electrons. And in this case, if we apply a drain voltage, a positive voltage on the drain terminal, what it would do is it would try to make this junction forward bias, but this junction is not neither forward bias nor reverse bias. And moreover, this uh, in between region is also a big region. So a significant, there would be no current, almost no current in the device. And the current is measured between drain and source. Do you understand this? That
So
if this,
it is like a capacitor.
sorry, what is capacitor?
So like there is two plate, one at top and one at bottom, and field is between them.
No, this you are, I guess, understanding, or this is not a plate. This is just a contact.
Okay.
Although you are right that there is a capacitance as well in this case, but that's a more complex capacitance. Let's not go into that right now. We are trying to understand the mechanism of the MOSFET, and the mechanism is that when the gate voltage is zero, in that case, if we apply a drain voltage, there will be no current, almost no current in the device. The current between drain and source will be zero. And on the other hand, if we apply a positive gate voltage, what this positive gate voltage does is that it repels the holes in this semiconductor here, and it attracts the electrons to the interface. It attracts the electrons to this oxide semiconductor interface. Do you see this? Now, like this, if this gate voltage is sufficiently large, a lot of electrons will be attracted to the interface. And these source and drain regions are also n-type material. They also have a lot of electrons. So this becomes as if there is a continuous electrons from source to drain. It becomes like a conductor, and there will be a current in this device if we apply a drain voltage. To summarize this thing, the current between the drain and source terminal is depending on the voltage on the gate terminal. If the gate voltage is zero, the current is not there. But if the gate voltage is positive, there will be a thin electrons and there will be a current in the device. On the other hand, if the gate voltage is negative, what happens is instead of electrons, negative voltage on gate terminal will attract holes, and again there will be no current because uh, this will try to pump electrons here, they will recombine with the holes, current will not be there. So the current across drain and source is there only when the gate voltage is positive, and that too a sufficiently good positive gate voltage that can attract a lot of electrons to the interface of the oxide and the semiconductor. Is this idea sort of clear or not?
Sir, so what is the use of that silicon oxide which we are using SiO2?
Yeah, this is question one. Anybody else has any other questions? And this is
Sir,
actually, I would say, this is, yeah.
Sir, we are grounding the
Yeah,
body of transistor because we do not want an excess charge on the body, right?
not that actually.
Sir, because when the
Excess, what do you
electrons
mean
will,
by excess charge?
sir, sir, could you repeat?
What do you mean by, yeah,
Sir,
what do
when
you
the
mean by
electrons
excess charge?
will go towards gate, positive charge will appear on the other side. Holes will concentrate downside.
Yeah,
So,
that way. Yeah, that way we do not want any charge to go to the downside actually. We want the charge to flow from drain to source, just these
okay.
two terminals. Yeah, you're right. Yeah, but there was a very good question, and the question was, uh, what is the use of oxide here? What do you think is the use of oxide here?
So if there is no oxide, then the electrons will move into the gate.
You're right, and vice versa as well. So the oxide works as an insulator. Insulator means that it will block any movement of charge carriers between gate and this region is known as the channel region. So this region between drain and source is known as the channel region, and the channel region is the active region of the device. So this small region is actually responsible for the entire transistor operation. And if this oxide is not there, in that case, on application of a gate voltage, electrons might flow from gate to this side, and it becomes pretty much like BJT or something like that. Or it might even short circuit these things as well. Okay. What
Sir,
is the
so why
advantage of
only
this?
metal oxide we are using? We can use anything like plastic even. So any insulator will work.
Yeah, that's next question. But why do we even need? Why do we need? Or what happens when oxide is there? So when oxide is there, there is no current that is going in the channel from the gate. But the electric field due to gate is controlling the charge in the channel, which is responsible for the transistor operation. So that's why this field effect term comes from, uh, because the electric field due to the gate voltage is controlling the charge in the channel, and the charge in the channel is responsible for the current through the transistor. Okay. So now the next question is why do we need the silicon dioxide here? Can it not be a plastic or something like that? So that's a question actually I would say that goes to the roots of the MOSFET. And the reason is that this idea of the MOSFET was there even before the invention of the BJT. So people knew that this kind of structure could work as a transistor. And this could be better than BJT as well. Because in this case, there is no current. In the case of BJT, there is a base current, which is a problem sometimes because it can reduce the number of charge carriers. We need to handle current on the third terminal. In this case, we just need to apply voltage, and it's like a capacitor we put on top of channel, and by one plate of capacitor, we are controlling the charge here. But so what I was saying is that this idea was there since 1920s, but the first MOSFET could be made in 1958, late 1958, almost 11 years after the invention of BJT. And your question actually goes back to that delay. This interface between the semiconductor and the oxide is extremely crucial actually. So the thing is that when a gate voltage is applied, a very thin layer of electrons is deposited here. This inversion layer is a layer of electrons in a p-type material. And please be careful that this is a p-type material. And in this p-type material, we have inverted this p-type material from a hole dominating to an electron dominating in this region. And this layer is extremely thin. This is few nanometers. Okay. So that's why this interface, the dangling bonds on the channel and oxide interface, they are extremely crucial because if there are lots of states there, so if this interface is not clean, the proper lattice matching is not there. There are interfacial charges may be there. Interfacial charges means that if there is a mismatch on the interface between two solids, some charges might get stuck there, and they can entirely spoil the operation of the MOSFETs. So a very clean interface between the channel and the oxide was extremely crucial, and a lot of insulators were tried for that. Ultimately, uh, what is done is that a silicon is deposited on top of silicon, and the silicon is then oxidized. So, so that's why this interface becomes proper. Because if there is a bond mismatch, then this thin inversion layer of electrons can be spoiled easily. And this whole
Sir, how do
transistor, this entire,
use,
yeah.
sir, how do we use
Uh,
this thin layer of electrons?
yeah, so this thin layer of electrons is there. Now, once this layer is there, then if we apply a drain voltage, then the drain current first varies like this. It becomes like a conductor in that case, a thin conductor. Because the source is n-type, the drain is n-type, and in between also there are electrons now. So it becomes like a continuous n-type material. Okay, so that way it behaves like a conductor, as you can see, that the current is directly proportional to the voltage, at least in the beginning.
This means because it was a minority carrier, so we do not want it to dissipate somewhere else. That's why we have put that metal oxide.
No, so if this interface is not there, good. In that case, there might be electric field, and this thin layer may be absent from some places. It may not be there. It may have irregularities. Two MOSFETs will not be similar to each other, so we cannot use them in a circuit. So those kind of reliability issues arise when this oxide is when this insulator is not properly lattice matched to the channel. Okay, because we need to build millions of transistors, or almost each of our laptops might have a billion transistors, and we need to make all the transistors pretty much exactly same to each other, or consistent to a certain standard. And if we have interfacial charges, or if we have mismatch at the interface, then no two transistors will be the same, and this entire electronic circuitry may be dysfunctional. So is this more or less clear, this part?
Yes, sir.
So this is the IV characteristics here of the MOSFET. And as you can see, these are the gate voltages, 3, 4, 5, 6. It means that if a positive gate voltage is there, it will create a thin layer of electrons, immersion layer, and that will allow electrons to flow from source to drain. So when let's say that we on the gate we have 5 volts applied, so this layer of electrons is there, and if we apply a drain voltage, as the drain voltage is increased, the drain current will also increase. But after some certain point, let's say at this point, the drain current no longer increases.
So
It
pointer
almost
is not visible.
sorry, is it visible now? I
Yes.
hope it is visible now. Yeah, so these are the IV characteristics, and these are various IV plots as a function of gate voltage. These are the gate voltages. And as you can see that a positive gate voltage creates a layer of electrons. And if we try to understand this particular case, when let's say the gate voltage is around 5 volts, in that case, this layer would be there. And if we apply a drain voltage, a current will be there in the circuit. So if we increase the drain voltage, the current will also increase almost linearly. But after a certain point, after this point, the current becomes saturated. It does not increase any longer. Okay. So why does this happen? This is my first question. Second is, I would like all of you to note down here that these characteristics are pretty much similar to the characteristics that we discussed in the beginning that are required for a transistor output. These characteristics are pretty much similar to these kind of characteristics. Do you see this? That a voltage on the third terminal is controlling the current between the two other terminals. So exactly the same thing is happening in the case of MOSFETs now. But the question is, why is this current saturating after a certain drain voltage? And I would say that if you understand this, then most of these characteristics will be clear to you.
Like sir, what happens is that like when Vg is constant, like it is 5 volts, so that it attracts some of the electrons, that is the least case. So when Vd increases, keeps on increases, then the electrons become the electrons present in that region become constant, so that this Id also becomes constant.
Electrons become constant means
Like so that region, that inverted region becomes constant pretty much because of that constant Vg, gate voltage.
but it is constant for all the drain voltages. So this
Sir,
Vg is constant for all the voltages, and according to what you are saying, that number of electrons will be constant for all the voltages.
sir, is it related to the maximum thickness of that the thin electron layer that is made as all the
Yeah, it
electrons go upward? There will come a point when there are no more electrons left as it is the minority carrier in the p-type region.
yeah. So something like this happens actually, and that's a good point that you have raised. So what happens is that as soon as so the gate voltage is constant most of the times. Okay. As soon as we apply drain voltage, what happens is that on this side of the MOSFET, the voltage difference between the channel and the gate starts reducing. Because if we are applying high drain voltage, the difference between gate and channel on this side, voltage difference is reducing. On this side, source is grounded. So on this side, the voltage difference between channel and source is maintained. But on this side, this difference is reducing. So it means that the number of electrons here on this side will now be less. So something like this starts happening because of the drain voltage, the net voltage that is felt by the electrons here is now reduced. So the voltage that the electrons feel here is Vg minus Vd. Okay, so that's why, and on this side it is just Vg. So the more number of electrons will be on this side, and the less number of electrons will be on this side. Do you see this point? This is quite an important point. And there comes a time when Vd becomes so large that on the right side of this channel is now absent, which means that the thin layer of electron is now terminating before the drain voltage. So something like this might also happen because of the large drain voltage here. Okay. Do you see this? And this is known as the pinch off. Pinch off means that the channel has been sort of cut off from the uh, in
Yeah,
between.
but why the ID becomes constant after this? We have no
Yeah,
we have no continuous stream left now.
that's a good question. Why is ID not zero? Should be the question. Is that what your question is?
Yes, sir. Yes, sir. ID should be zero because there is no continuous stream left.
No channel here. Yeah, but please remember this that this side, this drain channel, this drain body is a reverse bias junction. Okay, and this is n-type material. If we apply a positive voltage on n-type material, it is a reverse bias situation. and the depletion width is increased. And because of the depletion width, the electrons that are coming from the source side, they are now quickly swept by the electric field of this depletion region to the drain side. So it means that now the channel is reducing, so the current should reduce, but at the same time, uh, uh, they are getting quickly swept to the drain terminal as well. So the current does not increase, but it also does not decrease. More or less, it stays the same. That is because of the drift of the minority carriers, drift of the electrons to the drain terminal. So do you see this p-n junction theory and this field effect? Both of them are playing role in conjunction. And that's how this kind of characteristics are achieved in the case of MOSFET. This is the entire, or I would say this is the fundamental principle of MOSFET operation. So there are few key points here. One is the formation of this thin layer of electrons. Second is once the drain voltage is there, this thin layer of electrons is disturbed and a pinch off might be created. And third is that the electrons that are coming from the source to the drain side, they should in principle terminate here, but because of the depletion region, they are swept to the drain side. So the current does not increase, it almost stays the constant. And this thin layer of electrons is there because of the electric field of the gate terminal. That's why this is the field effect transistor, and the gate terminal is known as the control terminal. So gate is controlling the current between the two other terminals, between the source and the drain. And this is how the characteristics are achieved. If the gate voltage is very less, in that case, there will not be any thin layer of electrons, no inversion layer of electrons, and no current will be there. For a positive gate voltage, current will be there, but it will saturate after a certain drain voltage because of the pinch off in the MOSFET. So that is the essential physics of the MOSFET. And you would read this in detail in your, I would say, in your coming courses. But here my aim was to introduce you to this beautiful idea of an electronic device which has changed, I would say, changed the way the world works actually. And this is the mechanism of that device. Okay. Can you also think about a device which can work like a transistor, but or maybe a better than a MOSFET transistor? Okay, yeah, so think about that. And there is this notion of threshold voltage as well. The threshold voltage is the gate voltage. Remember, gate voltage at which this inversion layer is formed. So it is the gate voltage at which the current starts conducting in the channel. So below the threshold voltage, yeah.
सर हमारे कॉलेज कब खुलने वाले हैं आपको पता हो तो
Now we will come to that later. So I had a talk with, so there it seems to be a meeting today and a decision will be taken there. Yeah, so don't worry about that, but let's try to focus on what we have been discussing here. Uh, Threshold voltage is the gate voltage below which this inversion layer is not there and above which the inversion layer is there. So below the threshold voltage, this IV characteristics will not be there. It will almost be a zero current. But above the threshold voltage, this is how the IV characteristics look like. Yeah, I know you are pretty much concerned about opening the college, but it is not in our hands. Calling you back and I had a chat with somebody in the administration today, and they are saying that there is a meeting, an important meeting today, where decision can be taken about this. Okay, but I'm not sure. I don't know. To be honest, I am in favor of opening the colleges, opening the campus, and I regularly convey my opinion to the administration in this regard. Okay. So this is, and I know, as one of you pointed out, that your screen time is increasing, and that's not the only point. It's also about peer learning. The peer learning at home is zero, and it's there only when you are in the campus. So I am all for that, and I guess everybody is understands that. So that's why there will be some quick thing.
But sir, most of the other colleges are opening.
Yeah, IIT is also almost opened. Uh, if you come to Roorkee campus, there are a lot of students here still. So they were so the institute was calling students since I guess October, November, and a lot of students came back. But suddenly, due to the surge, it had to be stopped. And now, this since this wave is saturated or it has gone down, so that's why there is again reviewing this. Actually, last year, as far as my understanding goes, last year because of this COVID second wave of the COVID, there were some mishappenings in the students, and that's why the institute is quite concerned because last time they were allowing everybody to come back and things were happening, but again certain mishappening happened, and that's why they are and once any bad incident happens, the institute actually is held responsible for that, although it might be the students mistake, but the institute is held responsible. So that's why the institute is quite conservative in taking decisions. They take decisions when things are really under control. Okay. So coming back to the main thing, this is what in electronic devices, this is what we have discussed essentially. We have discussed the PN junction, the diodes, the BJTs, the MOSFETs. Although not too rigorously, but given the time constraint, uh, we try to understand the essential physics of these transistors or these devices and their applications. Now, let's quickly talk about the integration part. And during the history part of the electronics, we also talked about it. That integration is a process through which a lot of transistors, a lot of devices are fabricated on the single chip. And for modern day era, it is an extremely crucial part because if the integration would not have been there, we would not be able to have billions of transistors in a small cell phone. And this electronics revolution would not have been possible. So that's why this integration is quite crucial. It is about making multiple transistors on a single chip, compact fabrication. And there are four kind of integration. One is the small scale integration. This used to be earlier 1970s when we had almost 100 components on a single chip, around 10 gates. Then medium scale integration, 500, around 500 components on a single chip. Then came the large scale integration in which up to 300,000 uh, transistors were there on a single chip. And then came the VLSI, where we have about a million transistor or more than multi-million transistor on a single chip. So it is also an engineering achievement to be able to make this kind of number of transistor on a single chip. Nowadays, more than a billion transistors are there on a single chip. Okay. So this is just to give you an overview. Why do we need integration? Because the size is smaller, Integration also improves design. The speed is also fast. If we have all the transistors separated from each other, in that case, there are a lot of capacitances there. And by integration, and as you know, the capacitance reduce the speed of operation. So in the integration, we have low capacitance, high speed, low power consumption. Also, integration reduces the manufacturing cost. So this Moore's law that we studied in the beginning, which is essentially which says that the number of transistors will increase and the cost per transistor will decrease. That has been possible because of this integration. And these are some of the companies, VLSI companies, electronics companies that are working in India. Okay, so this essentially completes our discussion on electronic devices. Now we also need to discuss about electronic circuits, and I would not like to take this discussion in this class because you might already be saturated. Pinch off might have happened. So these are some of the electronic circuits. Just to give you a glimpse, these are some of the electronic circuits. And I guess most of you would be aware of these. First is the circuits made out of diodes. So we have half-wave rectifier, and a rectifier is a AC to DC conversion device. And then full wave rectifier, we have diode clipper, diode clamper, and voltage regulator using diodes. And finally, these op-amps, operational amplifiers, I would say these are more important electronic circuits, and all the previous ones you can understand on your own, but op-amp we need to discuss properly. And so maybe we'll take that up in the coming class. So I hope we would be able to have one more class to discuss this op-amp, because op-amp is an extremely important device, I would say. Even nowadays, uh, even in placements and in internships, many questions are asked about op-amps. Okay, so op-amp is that important. So we will have a basic discussion of op-amp in this course, but a more detailed discussion will be there in your second or third year. Okay, so that's all for the day, and thank you for your patience. And we would need